Generative AI has rendered traditional visual forensics obsolete. We must look past the surface into the mathematical wireframe of synthetic media. The bad Photoshop relied on human errors. Machine learning bypasses these tells, generating pixel data based on statistical probability. Analysis has moved from the investigation of captured physical light to the evaluation of mathematical approximations. To remain effective, investigators must adopt a diagnostic framework grounded in these mathematical signatures. We will now conduct a systematic walkthrough of the microscopic decoding errors left by generative systems. These systemic traces serve as the new evidentiary standard for identifying synthetic media. Our analysis categorizes these markers by their generative architecture, focusing on diffusion models and in-painting techniques. Establishing proof of forgery requires a transition to a strict probabilistic assessment model. This protocol provides the tactical blueprint required for the modern digital forensic toolkit. To understand AI artifacts, we first establish the mechanical baseline of traditional photography, shown here under the physics of reality. In a physical camera, continuous light interacts with tangible lenses and sensors. This interaction creates organic artifacts, most notably native sensor noise. Machine learning models operate within a purely digital architecture, where images are constructed from learned statistical patterns. These systems learn to mathematically guess the final visual outcome. They do not simulate the behavior of light, they approximate the final pixel grid. This absence of physical capture is the root cause of every detectable AI artifact. Generative systems operate by shrinking complex visual concepts into a compact mathematical state. This compressed mathematical environment is known as latent space. During the generation phase, the AI must reconstruct the image from this compressed state. This unpacking process is an approximation that consistently introduces microscopic decoding errors. These errors appear as over-smoothed fabric textures, unnatural repeating micropatterns, and the absence of native sensor noise. These artifacts are structural byproducts of the AI's compression and expansion cycle. The methodology matrix categorizes different generative threat vectors and their associated signatures. We start with diffusion models to analyze their specific generation methodology. Diffusion systems create images by repeatedly removing noise until a coherent scene appears. The AI learns an average path to build these images, which makes it difficult for the system to recreate true chaotic randomness. Investigators should look for overly uniform noise patterns, particularly in flat regions like skies or empty walls. Secondary signatures of diffusion include glowing halos or unnatural softness around sharp, high-contrast edges. Diffusion models consistently reveal their mathematical origins through this lack of natural physical irregularity. We now move to in-painting to identify the signatures of localized image alteration. In-painting involves generating new content within a specific zone of an existing, physically captured photograph. This creates a forensic boundary between the physically captured reality and the mathematically generated edit. The first signature of in-painting is lighting inconsistency. Generated objects often cast geometrically incorrect shadows or fail to interact with the ground at all. We also look for broken background structures. AI often fails to maintain the continuity of fences, wires, or hair as they pass behind the edited zone. Finally, look for a sudden localized shift in sensor noise patterns that occurs strictly within the borders of the edited area. In-painting fails because mathematical approximations cannot perfectly replicate the complex intersecting physics of a real-world environment. A significant operational risk exists when analysts rely on a single visual flaw. Digital interference can produce artifacts that mimic AI signatures. Factors like compression, beauty filters, and social media resizing create their own noise that can mask or simulate generative errors. Identifying an isolated artifact, such as smooth skin, never constitutes definitive proof of synthesis. A single data point provides a flag for suspicion, but it is insufficient for a forensic conclusion. Relying on isolated flaws leads to false positives and compromised investigations. Reliable detection requires a probabilistic assessment built on multiple independent data points. Forensic certainty is defined from the rigorous synthesis of mathematical data.